We are at lecture 47 today. Actually, if I remember correctly, we have a 72-day semester. That is, if class meets every day of the semester, you'd have 72 class meetings. And I think today is day 55 of the 72-day semester. So not the time to relax and kind of coast to the finish line. Now would be a good time to kind of pour it on and finish strong. Hope to finish up 5.2 today. I think we can do that pretty easily. Let's go through another problem the long way of the sigma notation. So we want to find, this is, I guess, technically 5.1, maybe right into 5.2. Kind of hard to separate. Let's take this parabola, and I tried to get one that was going to kind of be ugly, and if you have one of these on the test, it'd probably be a little simpler than this, so this is kind of worst case scenario. We want the area under this curve from x equals 1 to x equals 5. So our A is 1, the B is 5. Now the second way we're going to do this problem is to do this problem using integral calculus. First way is to use the sigma notation. So we have basically two ways to get the exact answer. Let's start with this method so we can get another problem like this all the way through in class. So, and then we'll get our kind of our three formulas: the sum of 1 from I equals 1 to n, the sum of I from I equals 1 to n, and the sum of I squared from I equals 1 to n. So they will become a part of this problem. Probably the best thing for me to say is just this transitional step is just to memorize what x sub I is. How do we get to the ith x value? We start at our initial value and we move over I delta x's. So if we want to get to x sub 1, we will move over 1 delta x. If we want to get to x sub 2, we'll move over 2 delta x's. X sub 5, we move over 5 delta x's. So there's the first way we're going to do area on this problem. So A is 1, B is 5, delta x. Somebody tell me what delta x is in terms of A and B and n.
0-ish. 4.
Oh, what is it always? What is delta x? What is the kind of the width of each little subinterval?
B minus A over 2.
Good. B minus A over n. Okay? Now, if it were 7 rectangles, it'd be B minus A over 7. If it's 5 rectangles, B minus A over 5. We don't know how many rectangles. We're leaving it open. There are n rectangles, and then the last step in this problem is we're going to let the number of rectangles or subintervals get infinitely large. So in this problem, A is 1. I times delta x, well, it's 5 minus 1 over n. So delta x is 4 over n. That's the width of each skinny little rectangle. Times delta x. Delta x again is 4 over n. We're going to start I at 1. Let it go to n, and then the last step, let n approach infinity. Is there any part of that that looks completely new to you today? Is that something we did yesterday? Blair?
We need to do one of these in the test.
We need to be prepared to do that, yeah. That's why we're doing this today. Because we've only done one, and it wasn't nearly as complicated as this one is. So I picked one that's got an x squared term and an x term and a constant on purpose, so we've kind of got it all in this problem. Any other question or issue with this? Now, how do we make this relevant to this picture? Well, we don't even have a picture yet. What is this thing?
Parabola.
Parabola. You could find the vertex by taking negative b over 2a, or taking the first derivative and setting it equal to 0. It's a parabola that opens up. I think the vertex is. Now, it goes up a whole lot quicker than this because of the 4x squared. But basically, we want the area under this parabola from 1 to 5. It's a lot more area than what it appears to be right there, because we're going to get a pretty large number for an answer. All right, how do we take the f of 1 plus 4I over n? How do you take the f of anything? Plug it back in. So everywhere we see an x, we're going to put in 1 plus 4I over n. So there's 1 plus 4I over n. That x is squared. 3 times x. And then we've got a 2 added on to that. Told you it'd be kind of ugly. Times 4 over n. Unfortunately, we do the limit piece last, so we kind of have to write that through the whole process, because the last thing we do is let n approach infinity. N is the number of subintervals. It's the number of little rectangles. All right, let's square this, and let's go ahead and square it and multiply by 4 at the same time. So the first term squared is 1 times the 4 is 4. When we square this binomial, the middle term is what? Twice their product, right? Mm-hmm. So the middle term would be
32I over n.
8I over n times the 4, so 32I over n. And when we have the last term of this binomial squared, it would be 16I squared over n squared, and we're going to multiply that by 4. So what is that?
64I squared over n.
Good. Thank you. Then we just distribute the 3 to each piece. 3 times the 1 is 3. 3 times 4I over n is 12I over n. One of the reasons that I want us to do this problem, and it is a possible test question, and I'll tell you the truth, it's a probable test question. Not this bad. But another reason is that I think when you do long procedures like this, it helps you to appreciate the shorter procedures. So when we do this by integrating and evaluating, and we would very easily be done by this point in time, you begin to appreciate those shortcuts a little more. Plus 2, and then everything inside the brackets is going to get a factor of 4 over n multiplied by it. So just tell me what to write down. What's the first term?
Can you combine like terms?
Yeah, let's do that too. 4 plus 3 plus 2.
9 plus.
So let's just call that 9, and we're going to each thing gets multiplied by 4 over n. So those 3 put together multiplied by 4 over n is 36 over n. So I'll just kind of keep track. We've taken care of those 3. What else can be put together? 32I over n and 12I over n. So how many I over n do we have? 44 times the 4. What is 44 times 4?
172.
Thank you. I over n. So we took care of those 2, added them, multiplied both pieces together.
What
by
about n squared?
over n squared. Thank you. Probably would have caught that when we get to the simplification formulas. It's going to have to be an n squared. And 64I squared over n squared, that's the only term of that nature. Multiply that by 4 over n. And
256.
256.
Yep.
I squared over n cubed.
And
All right, so it's getting a little bit easier. Still kind of a cumbersome process. What recommendation do you have as far as what to do next?
separate them into 3.
Okay. So we've got the summation of a sum, so it becomes the sum of the summations. Probably didn't plan ahead. Let me kind of put a line through that. So what things need to stay in to the right of the sigma notation in the argument position, and what things can we bring out in front?
I's have to stay.
Okay, the i's have to stay. Everything else can come out in front. So the i's are the scrolling variables that start at 1 and go to n. So that leaves a 1 there. And what do we have here? 176 over n squared. I has to stay there. And here a 256 over n cubed. And that leaves an I squared. What's next?
Well, that first term will cancel out the n.
Okay, so this we know what 1 added to itself n times is. 1 added to itself n times is n. That has nothing to do with n approaching infinity, by the way. It's just 36 over n times n. What about the sum of I from I equals 1 to n? That's consecutive integers being added together. Good. That is n times n plus 1 all over 2. So if you want the sum of the first 43 consecutive integers, how would you do that? What's 1 plus 2 plus 3 all the way up to 43? 43 times 44 over 2. Okay, quick and easy way to get the sum of consecutive integers. And what is the sum of the first n consecutive integers squared? Good. I know somebody is anxious to ask this question. Do you have to have those memorized? I will give you those. Okay? Now, the first one, I don't know that I'll give you that one. The sum 1 added to itself n times, I think I can hold you responsible for that one. This one, I'll write it out either in here on the board when you're taking a test, or that will be included on the test. And same thing with this one. And I don't think we'll use the other one, sum of consecutive integers cubed, which is really this thing, the quantity squared. All right. Was somebody thinking that question?
Yeah.
Yes. All right, 36 over n times n. Those n's reduce. It has nothing to do with n approaching infinity. So let's get that out of the way. I'm going to put the numerical things together, 176 over 2, and then the other n things together. Here we've got a 256 over 6. We've got n times n plus 1 times 2n plus 1 all over n cubed. So I think that's all we can do until we now let n approach infinity. As n approaches infinity, we can simplify that. And as n approaches infinity, we can simplify that. So this thing right here becomes n squared plus n over n squared as n approaches infinity. That's what's going right here. What is that? 1, right? If they have like degrees, isn't the limit the quotient of the lead coefficients? The lead coefficients are 1, so it's 1 over 1. So that 1 is going to go right here. And the other one, if I took n times 2n, the first term would be 2n cubed. And as we stated the other day, everything else is of lesser degree, right? So I'll just put dots there. Because all we need are the two terms that are the largest degree, numerator and denominator. And if they are the same, what's the limit as n approaches infinity? 2 over 1. And that is going to go right there. Sorry, I wrote down limit. We've already done the limit, right? 176 over 2, we decided that was 1. And 256 over 6, and we decided this thing was 2. Now it's all numerical, which we would expect it to be numerical. It's an area under a curve. So the i's and n's have kind of been dissolved in terms of this function and where we started and stopped the area for this function. 176 over 2 is what? 88. And 256 over 3. I think we're going to be stuck with thirds, right?
Mm-hmm.
So what is 256 over 3? 80. 85 and a third?
Yeah.
Is that right? So the end result, I think if we add those up, 209. Is that right? This plus this plus this, 209 and a third. So I told you my diagram wasn't going to be very accurate because I knew the area was going to be a large number. 209 and 1/3 square units of area underneath this curve from x equals 1 to x equals 5. Any part of that anybody wants to ask a question about? That's as bad, that's as ugly as I would give you on a test. Probably more uglier because it just takes too long to do that one single problem. Blair.
Can I see those slides a few minutes after class?
Yes. Anybody else? So we do get an exact answer, but it takes a long time to get that answer. Let's do the answer the way we're going to, after we go beyond section 5.2, the way we're going to do these kind of problems. And that is, we want the area under this curve, 4x squared plus 3x plus 2. We're going to integrate it or anti-differentiate it. Then we're going to evaluate it to basically start it and stop it where we want to start and stop the area. Now that took us 3 pages, maybe more. Most of 3 pages to do that. Got an answer. Not any step of that was not like really difficult, but it's just kind of cumbersome to do all that manual labor. So this symbol tells us that we want to do what? It's another S, but it's kind of accommodating everything we did in that Greek letter, sigma. We want to do what with this S? Antiderivative or integrate. Okay? So what's the antiderivative of 4x squared? 4x cubed over 3, or 4/3 x cubed. What's the antiderivative of 3x? 3/2 x squared, or 3x squared over 2. Antiderivative of 2. 2x. We do not need the plus c because we're going to do some subtraction. Whatever this arbitrary constant is, it would be the same in the subtraction. So we evaluate at the upper limit. And we subtract from that this antiderivative, this, I think we refer to it as a capital F of x at the lower limit. Sorry, that should be a 3. So we are 3 lines into this problem. We're already doing arithmetic, so the calculus is over much, much quicker than the other process. So 5 cubed is 125 times 4 is 500. 5 squared is 25, so there's 75 over 2. There's a 10. Everything that follows gets subtracted. So there is a 4/3. There is a minus 3/2. And there is a minus 2. Let's see. We've got 500 thirds minus 4/3. Takes care of that and that. 75 halves minus 3/2. And 10 minus 2. So let's do the thirds. 500 minus 4, 496 over 3. Let's do the halves. What, 72 halves? And the whole numbers, somebody check that, but I believe those are the correct numbers. If you add them together, you should get 209 1/3. Again, it's an area. We'll have other applications for integration, but our first application is that it gives us an area under a curve.
Do we have to have like units cubed or units?
You could say square units or units squared. Just know that it's an area. It's going to also give us other things, so I hate to kind of call it something now and then refer to that type of answer as something else later on. But it is an area. If you had your choice of which 2 ways to do, that's a stupid question. All right, so possibly one of those on the test, but shorter than that. And then you also have the way to check it, right? The way we just did that problem. In fact, that could be a problem that had 2 parts. Do it the sigma notation way, do it the definite integral way, and then you have a built-in check to the problem. All right, properties of the definite integral. Let's take a look at these and what they, I mean, I think we've probably already used all these. You would do this anyway. I'm going to put that in the middle. If you can tighten up on that, that'll make it a little bigger. Thanks. So what does this say if we have a c here? What can we do with this number c that we find in the integrand? You can bring it out in front, right? Didn't we also do that with sigma? So, and aren't these two basically kind of the same things? One is a finite number of things we're adding together. This is an infinite number of things. Now, why the b minus a? Well, if you bring the c out in front in this problem, what does it leave behind?
dx.
1 dx, or just dx. What is it that has 1 for its derivative? X. And what do you do to evaluate something from a to b? You take it at the upper limit, which would be just b, and at the lower limit it would just be a, which is what this is. Summarize number 2 for me. What do you see when you look at that?
Just separating it like we did in sigma notation.
Okay, we did exactly the same thing in sigma notation. If we had the summation of a sum, it became the sum of the summations, right? So these s's are clearly related, but this is now is an integral. So the definite integral of a sum is the sum of the definite integrals. So that shouldn't be a mystery based on what we've done to this point. Looks like the c has been factored out again, right? Is that legal? Well, it was legal with sigma. It's going to be there in every term, so we might as well just save it till the end of the problem and bring it out front. Go ahead and integrate and evaluate just like we did here and leave that c out in front. What's that say? Same as number 2, except now it's a difference. And really, you could say, well, isn't a difference really a sum? It is. It's the sum of the negative. So these two are, in essence, kind of the same property. These are in your book, but those, we've already done this, right? Didn't we integrate 4x squared separately from 3x and separately from 2? So you would probably do this if we didn't have these properties anyway. Jonathan?
If number 1 doesn't have a function of a curve, and you're going to get a numerical value, what's that value?
That's good. Let's get a picture of this right here before we leave this sheet. We want the area under a constant. Isn't that what that says?
Yeah.
Right? So I'll just put a number up there. I'll put 4. What's the area under 4 from A to B? Let's put in 1 and 3. So I'm just putting some numbers in. So that is our function. So our f of x is 4. What is y equals 4? Horizontal line. And we want the area under that horizontal line from x equals 1 to 3. So we have a nice, clean rectangle, right? How tall is that rectangle? 4 units tall. How wide is that rectangle? 2. Well, what is 4? Isn't 4 the value occupying that? Right? So in the problem that was given to us, wasn't that the c value? So we know the area is 4 times, I'm going to say 3 minus 1 on purpose here. And what are we supposed to get? Aren't we supposed to get c times b minus a? Isn't that what that is? C times b minus a. So it's about as simple of an area problem as we could have and still check it. It is a nice, clean rectangle. You know how to find the area of a rectangle in what? 3rd grade? Probably 3rd or 4th grade. You start doing areas in that class. All right, next sheet. Let's see what a picture of this would look like. Looks like the first one, we want the area from A to C. And then where this one stops, at C, we pick up at the same point, C, and then go on to B. What's another way of accomplishing that? Of going from A to C, picking up at C, and going to B. How about if we just went all the way from A to B? Where would that ever come in handy?
Non-continuous.
Okay, or we have, it's got to be continuous because we want the top of our region to not have any holes or gaps in it.
Where you have something negative and positive.
Okay, it could be where you had something negative and positive and you wanted to know how much positive you had versus how much negative. So there's one. Let's say our curve does something like this. We have curves that do things like that, right? So here is where we're starting it. Here's where it cuts the x-axis. And here's where we're ending it. Now, if we just went all the way from A to B, we're going to get the net difference of these two. I'm just going to assign some numbers. Let's say this is positive 5 square units of area, and this is negative 4 square units of area. If we did this problem, what would we get? If we went all the way from A to B, what would the answer be?
1.
It would be 1. Now, what is 1? How does that help us in the problem? I don't know. It might help you. That's the net difference of these two, or the net, I guess, sum. One's positive, one's negative. What might be more valuable to us, depending on the problem, of course, is to analyze this from A to C, and we get positive 5, and then take the area under the same curve, but now it's under the axis, go from C to B. Now it's negative 4. Maybe we want to know how much area is above the axis and how much area is below the axis instead of just the net difference of the two. So that might be valuable. And in some problems, they're going to actually ask you to take the absolute value of these two. Here's how the problem would be stated. How many square units of area are bounded between the curve and the x-axis? What's the answer to that question? 9, right? There are 9 square units of area bounded between this curve and the x-axis. Unfortunately, part of it's positive and part of it's negative. But depending on how the question is asked, you may want to take the absolute value of that and add it to the absolute value of that, because there are technically 9 square units of area bounded between the curve and the x-axis. All right, so part of the region is positive, part of it's negative. What's another reason that we might want to split it up at some intermediate point? Anybody? How about the curve starts out linear and then it takes over with some quadratic equation? And we want to find the area under this curve from A all the way to B. This is, you've seen these, right? Where we've got one line up here that describes the function for a while, and then you've got another line that describes the function from that point on, kind of a split domain function. It's still all f of x. We're still finding the area under f of x, but f of x changes. It changes at c. So here it's linear, here it's quadratic. Wouldn't it be advantageous in this problem to use the linear function from a to c and add to it the area under the quadratic from C to B? So here, this doesn't look like it. They look the same, f of x and f of x, but this is linear. This is quadratic. So if you have a split domain function, this also comes in handy. All right, some other properties that are in the book. You don't need to write them down. Let's just make sure we talk about all the properties that are handed to us in this section. So if f of x is 0, so that's our y values in our function, so they're all greater than or equal to 0, and we know that a is less than b, then we should expect that area under that curve to be positive, right? It's above the x-axis. We're starting at A and going to B. A is less than B, so everything is positive. Positive width, positive height. We should expect the area to be positive. If we have two functions and the f function is above the g function, or at the very least they're equal, and again A is less than B, shouldn't we expect the area under the f of x curve to be larger than the area under the g of x curve? Right? Might need a picture for this one. So our function is somewhere between lowercase m and capital M over the interval. So here's lowercase m. There's capital M. Let's say our function does this. So there is the integral area under f of x from A to B, whatever square units there are right there. So that's this guy right here. Isn't that number somewhere in between little m? Well, what is little m times b minus a? Isn't that guy right there? Right? It's lowercase m tall, and it's b minus a wide. So that's the smaller rectangle. The other end is it's the kind of the maximum value for the area under the curve is capital M times b minus a. Well, capital M times b minus a is the area of that rectangle. So this would be the small rectangle. This would be the larger rectangle. If our curve is bounded by those letters, lowercase m and capital M, certainly our answer for the area under the curve is bounded somewhere between that smaller rectangle's area and the larger rectangle's area. Does that make sense?
Could you add together this small one? How would you use that? How would you use that?
Well, it just gives a bounding. This is a kind of a bounding constraint to area. We may not know the area in a certain circumstance, but we know what it might be at the smallest and what it might be at the largest. So we kind of have limitations on the area. So if we know a curve connects little m somehow to capital M, we know where the area is at its largest and its smallest by this particular theorem. All right, the other thing that is in here, I think we've touched on it briefly, but we probably ought to do a quick example, and then we'll be done today. I don't know that we've looked at it to this extent where we've kind of broken it down, but there is, in this section, it's a little odd, to be honest with you, to go back to an approximating technique. But they address it here, so I want to make sure that we've done a problem all the way through. So the area under a curve, granted, we know how to find exact, but it's approximately this f of x bar. Didn't I mention that one time? Mm-hmm. Where that is not the left endpoint, nor is it the right endpoint. It's the midpoint in that subinterval. And we have various midpoints as we progress through the different rectangles, so they're still subscripted x bar sub I. So let's see what that would look like. Here's x bar sub I. It's the left-hand x value plus the right-hand x value, and we're going to take half of that. So we're going to go right in the middle of the left endpoint and the right endpoint. So let's do two problems. One where we want to approximate the area. Under this function. From x equals 1 to x equals 2. So y equals 1 over x looks roughly like that. And we want to go from 1, 2 would be a whole lot closer, but let me bring it out here. So there's the region that we want. Need another piece of information. Let's say we want n equal to 5. We want 5 rectangles. So if we take this distance from 1 to 2, which we need to in order to find our delta x, it is, in general, b minus a over n. And for this problem, what's the width of each subinterval? 2 minus 1 over 5, 1 over 5. So there's our first x value. I know it's a lot closer than that, but this is going to get cluttered in a hurry. So we're going to slide over 1/5 of a unit. So this is what? 6/5? We're not going to use 1. We're not going to use 6/5. What are we going to use to generate the height of the first rectangle? The value exactly halfway between them. So our first x value is what?
11/10.
11/10, 1.1. Is that okay? So our first rectangle is how tall? It's the f of 11/10 or 1.1 tall. How wide is that rectangle? 1/5. The second rectangle, well, the next value is what? 7/5. So there's the rectangle. What are we going to use to generate the height of that rectangle? The average of those two. What's the average of those two? It's the average of 6/5 and 7/5. 6.5/5, what would that be? 13/10. 13/10 is 1.3. Does that sound right?
Mm-hmm.
Shouldn't it be the middle of this one should be 1/5 of a unit from this one, right? Or 2/10 of a unit away. So the f of 1.5, the f of 1.7, f of 1.9. So this, if we were to add all these together, this would give us an approximation for the area under this curve. Now, the f of 1.1, I don't know that we need to go through with all the arithmetic, but let's make sure we know what the f of 1.1 is. What is our f of x? It's 1 over x, so the f of 1.1 is 1 over 1.1. One over 1.3, and so on, right? We would add all those together and get an approximation for the area. Now, if we were to do this, I've done the arithmetic to this level of accuracy. It's 0.6919. Now, let's take probably 30 seconds and do this problem exactly. Don't we want the area under 1 over x from 1 to 2? Okay, what is the integral of 1 over x? Natural log, absolute value of x. I don't think absolute value is going to come into play in this problem. Everything's positive. So it's the natural log of 2 minus the natural log of 1. Natural log of 1 is the power you'd raise e to get 1, which is 0. So the exact area under this curve, a whole lot quicker, right? And better, because it's exact, is the natural log of 2. Somebody from your calculator, send us out the door with a very good approximation of the natural log of 2.
0.693.
Okay? And we got pretty close to that. We got 0.6919. All right. We are done. Have a nice weekend, and I'll see you on Monday.